and welcome here to our virtual seminar at Bar-Ilan. Marlin Schaefer from the AAI Hanover and Leibniz University in Hanover. Marlin is now a PhD student working in the group where I was a postdoc at the AI with Frank Oma and Alex Nitz. And the group is one of the central groups doing gravitational wave analysis in the world, partly within LIGO, partly outside of LIGO. They develop or do a lot of development of ICBC and other tools for data analysis of gravitational waves. And now we have a chance to hear from them and from Marlin about improvements in machine learning for analysis of gravitational waves. Marlin has asked or agreed to take questions at any time during the talk. So feel free to raise your hand, write in the chat, or burst into the discussion if something is troubling or unclear, or if you have any questions. Marlin, take it from here. Thank you for coming. Good luck.
Yeah, thank you for the invitation. I'm very glad to be here and, well, to virtually be here and talk about what we've done in the past, well, year or so. This has been mostly my master studies, and then we did it after I graduated and continued on putting it into a paper, which we've now put on archive about 3 weeks ago. And I'll be telling you a little bit about that. So the title is quite long. It's Detection of Gravitational Wave Signals from Binary Neutron Star Mergers Using Machine Learning. And so to start off, let's dissect that title into its different parts. So I have to click here. So first of all, what even is a gravitational wave, for those of you who are not so familiar with that concept? So as you know, charged particles, when you accelerate them, they will emit photons, so they will emit electromagnetic radiation. And something similar happens when you accelerate massive particles. So they will emit, instead of electromagnetic radiation, they will emit gravitational radiation. So they will bend space-time, and these waves will then travel outwards. And so the waves, they actually have an observable effect on masses. So if you had a ring of test masses and a gravitational wave were now going through these, so in this case, through your screen or coming out of your screen, you would see this effect that the ring would be stretched in the y direction, then compressed in the x direction, and it would go back to a circle, be compressed in the y direction and expand in the x direction, and going back. So that's then a full cycle of the gravitational wave. And so that's the effect the gravitational wave detectors observe. So they're just interferometers where they observe change in the arm length. However, this change is really, really tiny. So it's about 10 to the minus 19 meters on a 4-kilometer arm. So for comparison, the size of a single proton is about 10 to the minus 18 meters. So we are looking at sub-proton changes in length of such a long arm. Okay, so to produce a signal that we can measure that's strong enough, we need masses that are being accelerated, and these masses have to be very massive. So there's a few things we have to consider. So if we want to have masses that are constantly being accelerated, then the best thing to do is put them in circular motion. And if we want to have really massive objects, then, well, it's best to have two massive objects and then they orbit each other. And so we are looking for stellar objects, so objects of stellar mass or above that orbit each other, to have any observable effect. Because any gravitational waves we could produce as humans, they're, at least for the, well, far future, even probably not detectable. Now, the second thing is these detectors have a very narrow, well, not so narrow, but they have a band where they're sensitive to. So They are sensitive to frequencies between about 20 hertz and about 2 kilohertz. And so that translates at 20 hertz, we would need an orbital period of the two objects orbiting each other of about 1/10 of a second. So these two masses would have to be very, very close to each other. Now, combining very massive objects with objects that have to be very close without touching, and you get objects which are very compact. So we're looking for objects which are, in a classical sense, either black holes or neutron stars. And these are the two main sources, at least the coalescing binaries that are searched for. You can have some other sources, but these are the main sources and the only ones we've observed so far. So we can have a system of two black holes, two neutron stars, or a black hole and a neutron star. So these are the three systems that we will be looking for. Now, how does such a signal look like? Well, it starts off very slowly. So in the top plot, you can see what the detector would output if there was no noise present. That's the phase and amplitude evolution of the signal. And below that, you can see the according frequency evolution. So you can see, if you look at the bottom plot, that in the first time span, the signal stays at a nearly constant frequency, at a very low frequency. And then towards the end, it suddenly starts to ramp up and grow very fast until it then levels off again. And that leveling off point is just where the two bodies touch and merge. So they don't have frequency afterwards. So that's the basic evolution. And the reason why it looks like this is simply the power that is carried by the gravitational wave is proportional to some power of the frequency. And so the higher the frequency, the more power is emitted. Now, on the contrary, the energy that is radiated away has to come from somewhere. So the only place it can come from is the orbital, energy. And so the orbit will shrink as the system emits gravitational radiation, thus increasing the speed at which the two bodies travel around each other, and then also increasing the frequency, which in fact then drives again the radiation. And so it's a runaway process. And you can see that the frequency rises up, but at the same time also the amplitude of the signal rises up. So that's what we call a chirping signal. So if you ever hear gravitational waves are chirping signals, that's what it means. It's just the same, a rise of amplitude and frequency at the very same time. Okay. Now, I told you that there's no noise in this plot, and the detectors obviously are noisy. And I see a hand. Please ask. Okay. There's apparently then no question. So if you now plot the noise of the detectors on top of that, and we can do that, we have something like this. So we see in blue now the detector strain, so that's the noise, but there's also the signal already in there. So you can see that the signal has very small amplitude. So overall, the signal is very, very tiny compared to the noise, and we have to somehow find that signal. BIU would never be able to do that. Now, practically, this is an unfair picture because we can reweight the frequencies and their power just based on knowing how the detector noise is shaped, which frequency has how much power just as a noise background. So we can reduce frequencies which are very noisy quite well. And then for the very, very strongest gravitational wave, we can actually see them by eye afterwards, but usually you have no chance of just seeing them. Okay, So I told you that there's two systems or three systems. So we can have two black holes orbiting each other. We can have two neutron stars orbiting each other, or we can have a neutron star and a black hole orbiting each other. And so why do we only look at binary neutron star signals? So the reason is simply, there has already been work done with machine learning which have looked at binary black holes. So it would be boring to just repeat that. And secondly, binary neutron star signals are a bit more interesting and in some parts more challenging than binary black hole signals. And so why are they a little bit more interesting? Well, they have no event horizon, which means that they can also emit other radiation than gravitational radiation. So when two neutron stars merge, they will at some point touch and even before that heat up, and that will emit electromagnetic radiation as well as the gravitational radiation. So if this electromagnetic radiation is strong enough, we might be able to detect that. In fact, the first binary neutron star waveform we have measured in the gravitational radiation, we found an electromagnetic counterpart, and that was able to very precisely pinpoint the location. So if you look at the plot here, it shows the different confidence intervals of different detectors. And so the LIGO detector and the LIGO Virgo detector are the gravitational wave detectors, and they limit the search to some region. And then another telescope, which then found the electromagnetic counterpart, was actually able to very much pinpoint the location. Now, the way these signals are detected very much depends on the model we have for them. So some people were a bit skeptical when the first gravitational waves were detected. And they were asking, okay, did you actually detect something, or did you just have your confidence in the model? And so having an electromagnetic counterpart kind of works against that, because now we have the gravitational signal and that matches our expectations. And we say, okay, this is a signal which might have produced an electromagnetic counterpart. So let's look for that. And then we looked at the position and actually found that signal, and it very well matched what we were expecting. So now we have two coincidences which describe the same system. So we are very confident that that is actually a gravitational wave. Not that we're not confident in others, but this is another confirmation for that. And also it gives, well, it explains a lot about neutron stars. So we can infer a lot of properties of the neutron stars from them, or at least restrict certain parts, which is called the equation of state. So how does the density of the neutron star behave? And we can constrain that with such signals. So that's why we're looking for binary neutron star signals. But detecting them is a little bit more difficult. So the reason for that is simply the following. So here is the same waveform I've shown you before, just a little bit smaller. I haven't told you that it was from a binary black hole. And I'm sorry? Okay. And so to the right, I will now show you a signal from
Marlin?
Yeah, sure.
I'm sorry, I have a question.
Go ahead.
You show here a time scale of roughly 1 second in total.
Mm-hmm.
Is that comes from a black hole event?
Correct, yeah. So
okay.
This plot right now, that's a binary black hole.
Okay.
That's basically the point I'm getting to now. So looking at the binary neutron star signal, that's a similar signal, so of equivalent strength in the detectors. We can see at first look, they might look very similar, but if you look closely at, especially at the frequency evolution at the bottom plot, you will see that they will go up to a lot higher frequencies. And that's simply because the masses involved are a lot smaller, so they orbit a lot faster. And so we would need to sample that signal at a lot higher rate to resolve the entire signal. And now also, this is something you can maybe not so much see in this plot, but the starting frequency of the signal is about 50 to 60 hertz for the binary neutron star signal. And for the black hole, it's about 20 hertz. 20 hertz just because our detectors start to become sensitive at that level. If we were to now zoom out and look for where the binary neutron star signal is at 20 hertz, we would see the following. So the binary black hole signal, which is on the order 1 second, is just very tiny compared to the binary neutron star signal, which is on the order of about 100 seconds. So we have to consider a lot more data points because we A, have a longer waveform, and B, need to sample it at a higher rate to be able to detect them. And that's very important, and we will come back to that later once I've introduced machine learning a little bit closer. Okay, now I've told you that's very difficult to detect these signals, but how is it done currently? Well, we use a technique called matched filtering. So we have a very good model of what we expect the signals to be. And so we can look if the data correlates with that template signal. And so what we do is we slide our template across data and convolve it at every point. And if there's only noise there, then that will average out to be roughly 0. And but if the waveform matches with some part of the data very well, it will go to some finite value. And thus, it will give a spike in the plot. So if you do that at every point, you will get a time series. That's on the x-axis is time, and on the y-axis, you have something that's called signal-to-noise ratio. And that will spike very heavily if you hit a point where the data matches the template. However, these are very sensitive to the template and how well the template itself matches with the signal. So we need a lot of templates to do that. And so in this plot, you can see all the templates that were used in a search for the first 2 observing runs. And there's about 100,000 points in this diagram. So each single point corresponds to a single template. And to now analyze the entire data, we need to convolve every single template with the entire data. And to do that in real time is computationally quite expensive, but currently doable. However, there's 2 things that will increase the number of templates we will need in the future. First of all, the detectors will become more sensitive at lower frequencies, and thus reweighting the signal-to-noise ratio we can extract from them, and in turn, therefore, requiring more templates to have a similar spacing in that space. And second of all, we're currently neglecting a few effects. So we're neglecting eccentricity. So we're only considering systems which are basically orbiting circularly. Then we're also just saying, okay, if both of these objects spin, they are either aligned or anti-aligned with the orbital plane, but we don't allow something where it's pointing in some random direction, because that would introduce precession and complicate the signal again. Or an effect which we've actually measured with the last published signal was higher modes. So currently we're only looking at the fundamental oscillation mode, but there are higher oscillation modes which are within the data, and including these would also increase the number of templates. And so the computational cost of the search scales linearly with the number of templates we use. And so in the future, it might break our computational budget to run the entire filter bank as a search to be able to keep up in real time. So that's why we're looking for alternatives in a way. So why consider machine learning? Well, other research areas have shown that neural networks are usually very well at adapting to unseen data. And as I've told you before, there have already been studies which have tried using machine learning algorithms for binary black hole data. And they've actually shown that if you train a neural network on data where the binary black holes are on a circular orbit, they can still detect something that's in an eccentric orbit, to some degree at least. So there's hope that we can build one machine learning algorithm, and then it will also adapt to other kinds of signals. Furthermore, they're known to be very computationally efficient. So what you do when you train the network is you basically shift the computational cost of the algorithm to a stage before using it. So the computational cost is shifted from the evaluation step to the training stage. And so evaluating the network is usually really, really fast. And so overall, the hope is simply that we can keep the computational cost of a search more or less constant, even going to future detectors or including other effects. And now there's also just the scientific curiosity and seeing, okay, there's this emerging field of machine learning. Can we apply it to our research field as well, or is that something we should stay away from? Okay, I've now talked about machine learning, but what is machine learning? So in principle, machine learning is just a way of saying, okay, I have some example data, I feed that to some computer algorithm. The algorithm will take that data into consideration and give me some other value for an unseen sample. So in principle, if you have a data point cloud and you use some fitting function, you're already using a machine learning algorithm because you're adjusting the fitting parameters of your fitting model to fit that data. And then you can also evaluate it at any point between or extrapolate or something like that. That's in theory already a machine learning algorithm. So neural networks are very similar in that sense, but let's look at what a neural network does specifically. So a neural network is a network of neurons. So we do have to consider what a single neuron does. And so in this picture, you can see an input vector A, which is fed into the neuron. And the neuron itself has three main parts. It has a weight vector W, it has a bias B, and an activation function F. This activation function is just a nonlinear function which is applied to the inputs, basically, what's applied to the weighted sum of the inputs plus the bias, just so the network can learn nonlinear functions as well. So the order of operations is simply you multiply the inputs with the weight vector in a scalar product, add the bias value, and apply the activation function to it. And now when you train the model, you just tune the weights and biases so that the entire network does what you want. So a neural network is an entire network of these neurons. And so the computational cost, again, the computational flow, again, is here from left to right. And you have your input layer, which is, okay, the entire network is structured in layers usually. So you arrange the neurons in layers, so it's easier to work with and mathematically becomes a lot easier. And so the input layer here is determined by the size of your input data. In our case, that would be a time series. So the number of samples in that time series would be the size of our input layer. And then the output layer is determined by what you want to get out. So in our case, we want to get an estimate of the signal to noise ratio. So we would, in principle, have a single output. We do have two, but I'll get to that later. So that determines the size of our output layer. And now what happens if you pass an example through is that you put your input into the input layer, that travels through the hidden layers and gives you an output in the end. The hidden layers are what really are the gist of designing a neural network. So you can choose any number of hidden layer. In this example, there's only one, but you can have any number. and they can have any shape and size. Now, what you do on any hidden layer is you connect all the neurons to the neurons on the previous layer. And then for the output layer, that's the same. And when you now train the network, you pass your example input into the network, and you observe what comes out in the end. And you compare that to what you know you put in. So you need to have a label for that. And you just simply take the derivative or the gradient of that function with respect to the weights and biases of the entire network. So you can see the network as a function of your input, the weight vectors, and the biases. And so it's just a function with very high dimensionality, and you try to optimize that with respect to the weights and biases, and try to minimize the error between the output of the network and the label you provide. That's everything machine learning or neural network training is. Other questions so far? Okay. If not, then I will continue on to why it's challenging.
Marlin, what is the extent of the time signal which you feed in? Do you feed like how long is this sequence?
So I'll get to that in a second, but it's 32 seconds that we're using.
So you start every time at every time point, then you take 32 seconds and then you shift it by one time step and do it again.
Not quite. I'll also get to that a little bit later.
Okay, yeah, sorry.
No problem. But basically we shift an input window. Okay, so that's exactly the problem that we have. So applying a machine learning algorithm in theory sounds quite simple because you just take your time series and input it to the network, then you provide a lot of examples and it should optimize well. However, the problem is that neural networks tend to have problems when the input when the input has too many data points. So it's fine usually to have 1,000 or order 1,000 inputs, but as you go towards 10,000 or even 100,000, the network stops to be able to optimize for that. And so that's the problem why you can't just generalize binary black hole data to binary neutron star data, because binary black holes, they are on the order of 1 second, the signals, and you can sample them at quite a low rate. So you are on the order of 1,000 input samples. That's fine and that works well. But for binary neutron star signals, you are on the order 100 seconds and you need to sample that at least 4 kilohertz. So you're very quickly at something like 400,000 samples. And so to get around that issue, there was one publication that actually looked at binary neutron star signals in the context of machine learning. And the way they resolved that problem was just taking the first 2 seconds of the signal instead of the entire signal. And that enabled them to not only train for binary neutron star signals, but also differentiate them from binary black hole signals and obviously noise. And that worked to some extent or pretty well. However, they use pretty loud signals. And the problem with that approach is that you throw away a lot of the signal. So you lose about 50% of the information that is in the data. So the way we approach it is we try to keep as much of the information in the data as possible. So we settled on 32 seconds of input data and just use the properties of the waveform to reduce the number of samples we can use. So on the top, you can again see the entire signal. And on the bottom plot, you can see the black line is the frequency evolution. And now we split the waveform or the data into different parts, each color representing a different part. And we sample each part at a different rate. So in the bottom plot, the height of the colored boxes represents the sample rate of the segment we are looking at. And so we start the first 16 seconds, we sample at 128 hertz. So that's enough to resolve 46 hertz of the gravitational wave. So if the gravitational wave doesn't exceed that, we are fine to do that. And we halve the duration of the next segment, but double the sample rate. And we keep doing that until we reach the last second, which we sample at 4 kilohertz. And so to resolve the entire signal, the black curve on the bottom plot has to stay within the colored boxes at all times. So that's the basic principle we applied. And doing that reduces the number of samples we require to resolve the entire waveform by a factor of 9, about 9, over just sampling the entire waveform at 4 kilohertz. And so now I want you to remember that different parts represent different colored boxes. So if I talk about parts on the next slide, I refer to the different colored boxes, so the different parts of the signal.
Where again does this factor of 9 come from?
So you can reduce the number of samples in the first 16 seconds by a factor of, okay, I'm not sure, 40, I think, or something. But that's only a part of the entire signal. And you can reduce the number of samples in the second part, that the pink part here, by a factor of half that, right? Because you sample at double the rate. And so overall, if you sum it all up, you use about only 1/9 of the samples. Is that clear?
And the binning is based on equal power in each frequency and time range, or some factor between F and T?
We use the time series waveform, and then we just simply assume that the peak amplitude is in the middle of the last second, and from there we say, okay, we go back 31 seconds or 31.5 seconds, and then the first 16 seconds we just simply say, okay, if the binary neutron star signal was here, then it would have a frequency range between 20 and 60 hertz in that time frame, right?
Does it depend on the masses of the neutron star, or do you assume a constant mass for all neutron star mergers?
No, we assume mass between 1.2 and 1.6 solar masses, and for those, I think it stays within that band. Okay, so I'm now going to show you the architecture of the network, so how the neural network looks like, at least a high-level overview. And so at very first, it seems very confusing, but it's actually very self-similar in a lot of places. So the computational flow here is, again, from top to bottom. So the input goes in at the top, and then at the bottom, you get your 2 outputs. And then you can also split it vertically into different columns. And so each column is basically the same, or is the same architecturally. So I want to draw your attention to the leftmost column, and we start at the very top where it says input 1 signal and input 1 noise. So we store signals and noise samples separately on disk, and they are already resampled correctly to fit the format that we need. And now input 1 just refers to part 1 of the signal I've just shown you, so to the first colored box. And then the first thing that happens for the network is it adds those 2 together. So overall, we have the total strain of a simulated detector output, right? So the entire rest of the network, so everything that has tunable parameters, only sees the sum. So that's very important. And you can see it splits up into 2 parts. One arrow goes into something called TCN, which stands for Temporal Convolutional Network. And we train that to recover the original signal. So we train it to denoise the input data. And we add that denoised signal back onto our input data so that we amplify any signal that might have been in there. And we pass that to a few pre-processing layers, which are just technically good for the network to have. That's some other research. And then we pass it to the main, well, workhorse of this network, which is called the inception res block. And that's, again, a very special kind of network using inception architecture. Yeah, it's just an improvement over a few other architectures that have been used. And so that's what's doing the main work and the main analysis. And so then each part of the signal gets passed to its own column and gets analyzed on its own. And after it's been analyzed, we just combine two neighboring parts and analyze those again with a different inception res block. And so we do that until we are left with a single column, which we then apply some post-processing to, which then gives us two outputs. One, an estimate of the signal-to-noise ratio that's in the input data, and two, a p-score, which is just the value between 0 and 1, and gives the confidence of the network that there's a gravitational wave there or that there's no gravitational wave there. It's not a probability, but just a confidence level of the network. Okay, so I've told you before that we are very strict on how long the data is that we can use. So we use 32 seconds. In this plot, it says 64 just because it's an older version, but the concept is still the same, so I didn't want to remake the plot. And so how do we apply it to a long stretch of data? Because that's what we want to do if we build a search, right? We want to see where in a long stretch of data is there a signal. So we just take the input window and shift it across the data. And so we shift it not a sample at a time, but we shift it by plus minus a quarter of a second. That's just due to the properties of the training set we chose. And so at every stage, we get an output for the p-score and the SNR. I'll only go into the SNR now because that's easier to understand, but the concepts are the very same. So you can apply the same concepts to the other output as well. And so now we get this time series of signal-to-noise ratio, and it stays at a very low level if there's no signal there. And once there is a signal there that aligns well in the input window, it will spike. And now the question is, how do we determine which is an event or not? So what we do is we apply a constant low threshold, and then we mark every point that exceeds this threshold. But now what we have to do is, because we expect that a real event would trigger, would produce points that are above this threshold for multiple consecutive times, we need to apply some clustering. And the way we do that is we just start at one marked point and look within plus minus 1 seconds. Is there another marked point? If so, add that to the cluster and expand the boundaries and continue that process until there's no marked point within plus minus 1 second of the cluster boundaries. And this choice of 1 second is just a fiducial choice. We've just made it and then went on. And so we get a series of clusters, and to say now, these we then call an candidate event, and we need to now assign the time and the signal-to-noise ratio to each event. The way we do that is simply going through each cluster and looking at the time and the value where the SNR is maximal in that cluster. So I don't know if you can see that now, but there's now a few blue lines, which are very small. So we say, okay, every event has now a time and a value. And now we can use that value to determine how significant the event is. So we can say, okay, a event which has SNR 6 is less significant than something that has SNR 20 attributed to it. You can do that a little bit more thoroughly and saying, okay, how many false alarms do I get at a certain SNR level, right? So that's what we are coming to now. So that's the results section. I want you to remember that it's very important that you test the network by applying it to a long stretch of data, by actually shifting it across and specifying a clustering algorithm. Because previously what people have done is just use different samples where there's either a signal there or it's just pure noise. And they just counted, okay, how many signal samples were missed and how many noise samples were classified as signal. And that doesn't take into account if the window only contains parts of the signal, or what happens if the network predicts that there's a signal for one point, then for the next point it says, okay, there's no signal, and then it again says, okay, there is a signal. So how do you handle that? Are these two events, or is that a single one? And so measuring the false alarm rate in the way we do it, just by applying it, specifying a clustering algorithm, and then comparing it to the injected values, so to signals we know we put in, increases the false alarm rate over that is measured on such a discrete set where you have either a signal or no signal by at least a factor of 2 up to a factor of 6 or 7 we've measured on our tests. So here are the false alarm rates. And I want you to only look at the blue curve. The yellow curve is not so important for us now because it's less performant. And on the y-axis, you can see the number of false alarms you can expect for 1 month of data. And on the x-axis, you can see the signal to noise ratio threshold. So an event with a signal to noise ratio of, let's say, 8 would occur about 100 times in a month and would just originate from noise. However, a signal with SNR 10 would only occur about 10 times a month. Now, we measured these down to about half a false alarm per month, so 1 false alarm per 2 months, because that's the point where current searches actually send out alerts. And yeah, that's something we would like to reach in the future. Now, you can see that the false alarm rate drops very steeply until it hits the false alarm rate of about 10, and then it levels off significantly. And that will be important in the next plot. But I only want to mention very briefly that in principle, we can drive this false alarm rate down to 0 just by choosing an arbitrarily high threshold. So saying, okay, we only count signals which have an SNR greater than 1 million as detection, then, well, we are probably not going to get any false alarms. However, any signal that is in the data, we would probably also not detect because, well, we won't have a signal with an SNR of 1 million, at least not anytime soon. So it's very important to say, okay, how sensitive am I to signals as a function of the false alarm rate, which is now the second plot. And here you can see the false alarm rate on the x-axis, lower false alarm rates are on the right, higher false alarm rates are on the left. And on the y-axis, you can see the sensitive distance in megaparsecs. So that's the average distance out to which we can detect a binary neutron star signal. And so you can see that it drops initially very steeply. And oh, we're only looking at the blue and yellow curve for now. So it initially drops very steeply and then levels off a little bit before then dropping again very steeply. Now the blue curve shows if you only use the SNR output to generate detections or candidate events, let's say, and the yellow curve is only considering the p-score output to do that. You can see that for high false alarm rates, they agree very well, but at low false alarm rates, the SNR output performs considerably better. And now at a false alarm rate of about 10 per month, which was the point where the previous curve leveled off, we now see a sudden drop in sensitivity. So that's where our search starts to become a little bit shaky. So we only consider our search to be stable about down to a false alarm rate of 10 per month. And there we have an average sensitive radius of about 130 megaparsecs, which is not great, but at least a start, I would say. Now, the green curve shows the PyCBC live pipeline, or an estimate of their sensitivity. And that's one of the searches that's currently applied in the first, in the second observing run and the third now as well. And you can see that they are a lot more sensitive at a lower false alarm rate. So we are not yet as sensitive or comparable to methods that are already existing and working well. Okay. However, that's not the only thing we were trying to do. So we are trying to do that also quick. So we are trying to do that speedy. And so let's look at a few speed factors. So how quick is our search? First of all, we have the training time. So it takes about 5 hours per epoch. And an epoch is just taking the entire set of training examples and passing it through once. So why do you pass the same set of examples through the network more than once? Well, if you start training, you have the first example, you put that into the network, and the network just puts out a random number. Based on that random number, it will then improve the weights a little bit. But now you don't really know, did you improve it well on that example? So if you pass it through a second time, you now have a network that has been trained on a lot of data. So you can say, okay, now the network should give me something that should be at least roughly right. So you have a lot better understanding of the error that's attributed to that, because you don't output a random number anymore, really. So that's why you can pass the same data through multiple times. And usually you train these networks for a few hundred epochs. However, we trained it due to time constraints only for 5 days. And we also had some other issues during training, which limited our training time. But yeah, so it takes about 5 days on a very high-end GPU to train this. To evaluate a single sample, so to evaluate a single window position, we take about 206 milliseconds. However, that ignores all pre-processing that would be required. So that's using already correctly sampled data, and it also doesn't attribute for whitening the data, which is just a process to reweight the power of different frequencies to make signals more prominent in the data. But just considering that, that would be fine if we were to ignore the pre-processing cost, because our search takes about 206 milliseconds, but the time step it processes is about 250 milliseconds. So we are a little bit quicker than real time. However, PyCBC Live, which is the pipeline I've just talked about, the search, is also able to process such signals in real time. And it's doing so on even less computational resources, just using a template bank that's equivalent to what we are searching for. So we are neither as sensitive nor as computationally efficient. So I guess both of these boxes have not been ticked. Last straw of hope would be to look at the latency. So that's the time between the signal arrival and outputting a alert. So that's the time you really want to minimize. And there we have an average latency of about 10.2 seconds. PyCBC Live uses about 16 seconds, so we're a little bit quicker there. However, you can just drive their latency down by increasing the computational resources you allocate to the search. So we might not win there as well. However, we are using a very basic clustering algorithm, and it's not optimized at all for latency. So choosing a different one, we think that we could get this down to about 1 second of latency. However, this is also still neglecting any cost for pre-processing the data. So maybe that balances out. We haven't tried that yet. Okay, now there's one last thing we can compare ourselves to, and that's the one other work that has tried to do binary neutron star searches with machine learning algorithms. And so that's what I'm showing here. The blue curve is their work, and you can see they generate their results at a false alarm rate of 7,500. You do have to take these plots with a grain of salt, because they used something they call the peak signal to noise ratio. And they said, okay, to convert this peak signal to noise ratio to a normal signal to noise ratio that matched filtering would output, you have a conversion factor of about 13. However, we measured that on binary neutron star injections and found a conversion factor of 41 instead, which is quite significant. And also we are using a 2-detector network, and they were only using a single detector, which again gives us a factor of square root of 2 about in signal strength. So we rescaled their data according to what we found, okay? Just to keep that in mind. But if we take that as a basis, then we can compare our network at the same false alarm rate, so at 7,500. And in gray, you can see the training range of our network. So that's the training examples it was given. So we gave it examples between signal to noise ratio 8 and 15. And within that region, we improve the sensitivity by about a factor of 10. For signals below SNR 25, we are still about, on average, a factor of 6 better. But above that, we're being outperformed. So our network doesn't generalize well to very strong signals. So that's an area we could improve. And we think that just by increasing the range in the training sample to also include higher signal to noise ratios, we might be able to just eliminate that and be better at every stage. But we haven't tried that, so we are not sure. But that's not the only thing we can compare. So we also tested to very low false alarm rates of 10 per month. So that's about 3 orders of magnitude below what they were testing. So there we can still, within the training range for our best output, find an improvement over what they've seen. So to conclude, maybe, we've introduced a new way to resample the data to reduce the number of samples that are required. We introduced a new architecture, and we improved with all these steps the performance of the best known neural network to analyze binary neutron star data. However, we also showed that it's not yet at a stage where it's comparable to known searches or traditional searches. So there's a lot of research that can be done in that sense. However, we also think that it might be worth pursuing because the lower latencies actually do seem to be quite good, and the generalizability to different signals might also be a great thing. And finally, we also want to say, okay, it's very important that you give the results in a way that is comparable not only to other machine learning algorithms, but also to all searches, so traditional searches as well. Yeah, and with that, I would like to thank you, and I'm open for any questions.
Marlin?
Yep.
I have a question regarding one of the first plots when you compare to the PyCBC.
You mean this one?
Yeah, exactly.
Mm-hmm.
Can you summarize in a few words when should I rely on the PyCBC and when should I rely on the machine learning that you used when I'm looking at this plot?
You should basically rely on the PyCBC at all times, I would say. It's
okay.
Just basically showing that we're worse in every sense, so that there's still a lot of things we have to do to improve what we're doing to be able to be on a comparable level.
Okay, I see. Even though the PyCBC is not relevant to false alarms around 10,000.
Oh, you could certainly run a PyCBC live pipeline at a false alarm rate of 10,000, and you would basically have a sensitive distance up to a few gigaparsecs. But the thing is, you don't want to run a search at a high false alarm rate, because a high false alarm rate means that you would notify astronomers for, I don't know, 10 signals a day, of which none are relevant or actual detections, and you wouldn't want to do that.
Okay, thanks.
So in a sense, it's not surprising you're you're doing less good than PyCBC. PyCBC has been developed and trained and tweaked for 15 years to find these signals, and you just have a naive neural network out of the box trying to do the same thing. But the question is, well, on two sides. One is, how can you improve the model that you're feeding into the network, and training it on, and give it a little more human intelligence rather than machine intelligence to try to do better? And the second question is there a field where you can outperform PyCBC because PyCBC was not trained for it? For example, can you handle more neutron star equations of state and tidal effects and eccentricities and wider ranges of parameters in this way, as you hinted in the beginning, which PyCBC can't do?
Okay, so to answer your first question first, the way you could improve is probably just using a lot more signals and a lot more input data. Because right now we're using about 25,000 different signals. If you consider a usual template bank, it has a few 100,000. So increasing that number would probably help a lot. But it would also increase the training time. So you have to make a trade-off there. And also you should have about the number of training samples as you have trainable parameters, or even more than that. And that's currently not the case for us. So these are two main points which you could improve. And you could also improve just the architecture itself. Right now, it's just very, very complicated, and I think it's overcomplicated. So you could do a lot better in that sense. Now, regarding your second question, I'm not sure if we would do better two different signals. So we have only tested binary black hole signals, and we were basically not sensitive to them at all. Using different equations of state and different, well, maybe different sources, that might be interesting. We haven't tried that yet, but considering that it was struggling to generalize to strong signals, right now I would doubt that it would generalize well to other kinds of sources or other kinds of signals. But yeah, the hope would be to simplify the architecture, and then that would probably also retrieve some of the generality.
Any other questions? Okay, if not, then let's thank Marlin again. I'm turning off the recording, so if anyone wants to ask for anything else offline, off record, you're welcome to hang around.